A rectangular storage container with an open top is to have a volume of 10 meters cubed. The length of its base is twice the width. Materials for the base cost $10 per square meter. Materials for the sides cost $6 per square meter. Find the cost of materials for the cheapest such container. So we're trying to optimize the cost of this container. Let's draw the container to better visualize it. It's a rectangular box container. So it should look something like this. Jeez, my pen is lagging. It should look something like this. So with this box, we know that the volume is equal to 10 meters cubed. We know that the materials for the base cost $10 per square meter. The materials for the side cost $6 per square meter. Find the cost for the materials for the cheapest container. We also know the length of its base is twice the width. So I'm going to denote this is length and this is width. And the length is equal to twice its width. Since we're optimizing the cost for this, let's create a cost function. So we can actually optimize it. So the cost for this is equal to $10 per square meter for the base. So there's a base which equals the length times width. So $10 times length times width. And a side note, a property of a rectangle box is that each opposite side has the same area. So the base would have the same area as the top. But since it's an open box, we will not include the top's area. I mean, an open box means that there's no top for the box. Now there is another side, which is this side right here, which is height times width. And now, like I said, each side has opposite, right? And also the sides cost $6. So it's, since there's two of these, 2 times $6 times height times width. And the same thing for this side, which is length times height. So it's 2 of these times $6 times length times height. So the problem with this is, to optimize, we need one variable in this. We can't optimize with 3 different variables. So let's use different relationships we know about this box to have one variable in this cost function. So we know that the volume is 10 meters cubed, and we know that the length is equal to 2 times the width. We also know that the volume equation is equal to length times width times height. We'll sub in 10 over here, and in the place of length, we'll sub in 2 width. This will allow us to isolate for h. So h is equal to 10 divided by 2 width squared, and h is equal to, simplified version is 5 over width squared. Now with all this information, we can plug it into this formula, the cost function, which will allow us to finally optimize it. So 10 length, we sub in 2 width times width plus 2 times 6, which is 12. For height, we sub in 5 over width squared times width plus 12. Length is equal to 2 width, and then height is equal to 5 over width squared. We can further simplify this by making this 20 width squared plus width over here and width over here cancel out, so it becomes 60 over width plus width here cancel out. 24 times 5 is 120, so 120 over width. This can further be simplified to 180 over width. Now that we have this simplified cost function, by finding the derivative of this and setting it equal to 0, we can find the critical points of the cost. So let's find the derivative of this. So the derivative of this, we bring this 2 down, 40 width plus, minus 180 over width squared. Now if I found the derivative of this, now I set it equal to 0 to find the critical points. Oh, also, I forgot to set restrictions on the width. So the width, it has to belong to a number greater than 0. And the reason for this is the volume of this has to be 10 meters cubed, and if it's anything less than 0 or 0, it runs the risk of having a volume of 0 and a volume of a negative number, which shouldn't be the case. It should have a 10 meters, and it can go up to infinity as long as the length and the height proportionally match the number. So this is the restrictions for the width, and anything solution that we get that's not in this domain, we count it as an extraneous solution. So now that we know that this is our cost function, we'll set it equal to 0. Wait, I should set a common denominator for this cost function, so it becomes easier when I set it equal to 0. So becomes 40 width cubed minus 180 over width squared. Now we set it equal to 0. We cross multiply the width squared. So we're left with 40 width 3 minus 180 becomes width 3 equals 180 over 40. 40, and then we cube root both sides. This should give us a width of 1.65 meters. But so now we're not done just yet. Now that we found the width, we can plug it back into the, oh, by the way, our width fits in our domain, so that's a very good sign. And we can plug this width back into our cost function to find the cost, because we're not actually looking for the dimensions. We're trying to have the cost of the materials for the cheapest such container. So let's plug it back into the cost. So cost is equal to 20 times 1.65 squared plus 180 over 1.65. And now that we have this, let me just calculate it. So the answer should be 163.5408, but it's dollars, so it's $163.54. This should be the cheapest price for this container. Okay, question solved.